last bit of probability that we're going to discuss involves some applications of the fundamental counting principle, some special cases. And the first one we're going to look at is permutations of objects. So starting with an example you won't find in your book, suppose we have 10 people waiting in line to enter the Apple Store. How many different line orders are possible? So I would want to think about, here is my Apple Store. And I would lay out a blank for each of the 10 positions in line that are possible. The line that represents first in line is actually here, closest to my Apple Store. And if there's 10 people standing around who want to get in, then there are 10 possible people who could be first in line. Now, once I've chosen one of those 10 people to fill this spot, there are only 9 remaining people who might fill this spot. And once I filled this spot, there are only 8 people remaining who could possibly be selected for the third spot, and so forth right down the line. Fundamental counting principle says we would multiply all of these up to figure out how many ways we can line up these 10 people. Now, the good news is you don't actually have to pick up your calculator and type in 10 times 9 times 8 times 7 and so forth. There is a notation that mathematicians use to summarize this idea of starting at 10 and counting downwards all the way to 1, multiplying those factors together. And that is this. It looks like an exclamation point. It's known as the factorial symbol. When you see 10 factorial, that means exactly this. Start at the number 10, count down to 1, and multiply all the factors together. In a separate video, I'm going to show you the different places you might find this on a calculator. So you can type in 10 and put the factorial symbol at the end of it, and it will multiply all of these together, giving you this number. So there are 3 million different ways that I might line up these 10 people. That's an example of a permutation because the order was important. There was a first position and a second position and a third position. And, if I have curly hair guy in the first spot and mohawk man in the second spot, that's a different order than if I reverse those and curly actually ends up in the second spot and mohawk is first. Those are different possibilities that would need to be counted. So again, order is important. Now, in the next example, suppose there are 10 people hanging out near the Apple Store, but only 7 are going to be allowed into the store before closing. How many different line orders are possible? Again, I've got my Apple Store, and this time I'm going to put out 7 positions for people to wait in. In the first position, there are 10 people hanging out. So I would want to start at 10 and say there's 10 choices for the first spot. Of course, again, once somebody's standing in that position, then there are only 9 choices for who can be second, followed by 8, followed by 7, 6, 5, and 4. Now again, you could just type in all of this into your calculator. However, we do have a shortcut that's built into your calculator for this as well, and that's using the permutation symbol. Again, it's going to be located in different places on different calculators, but what you would be looking for is usually labeled NPR, and the P is going to stand for permutations. And what all calculators will have in common is you have to put in a number before the symbol and one after. The number before the symbol always represents the total number of objects that you're arranging. And the number on the right, which is represented by the variable r, is always the number of objects to use. So in other words, in this situation, the total number of objects are my 10 people who are waiting outside the Apple Store, then the capital P for permutation, And how many objects did I want to use? 1, 2, 3, 4, 5, 6, 7. So this multiplication would be represented by 10p7. Now, the common area of confusion here is students very often will want to put 4 here. And they want to read the notation as, oh, start at 10 and go down all the way to the number 4. That's not how the notation works. The number on the left is the total number of options you have, and the number on the right is the number of positions that you're looking to fill. So if you type this into a calculator, it lowers the number of possibilities down to 604,800. Let's look at one other quick example. Find the number of ways of forming 4-digit codes in which no digit is repeated. I want to create a 4-digit code. If you remember from previous examples, there are 10 digits. So for the first spot in the code, I have 10 choices, the numbers 0 through 9. If I'm not allowed to repeat any digits, whatever digit I put in that first spot, I cannot use in the second spot. So therefore, my number of choices reduces to 9. Then it reduces to 8, and then it reduces to 7. Fundamental counting principle says we're going to multiply those up. And again, the shorthand notation for this would be the permutation, because the order of these digits certainly does matter. When you're entering a code, you have to put the numbers in the right order. We started at the number 10, and we filled 4 positions. So if you were going to type this into the calculator, you would do it by hitting 10p4, and that gives you 5,040. Now, before technology was as common as it is today, mathematicians used a formula to calculate this 10p4. And you're going to see that formula down here below. We'll take a look at it in just a second. To summarize, a permutation is an ordered arrangement of objects. The order matters. The number of different permutations, if you're going to use all n objects, is known as n factorial. The number of permutations of n objects, if you're not going to use all of them, so notice r is smaller than, or it can be equal to n, is found by calculating npr. This formula, let's take a look at how this works. So before technology, if you wanted to calculate 10p4, okay, we could technically just multiply this out. However, the formula says that the number on the left is my n, the number on the right is my r, and substituting, I would have 10 factorial in my numerator, n factorial, and then n minus r would go on the bottom. N is 10, minus r is 4, factorial. 10 factorial, again, is 10 times 9 all the way down to 1. And 10 take away 4 factorial would be 6 factorial. And 6 factorial would start at 6 and go down to 1. And then what you'd be able to do here is take a little shortcut, cancel off the 1s, cancel off the 2s, because 2 over 2 is just a version of 1. 1 over 1 reduces to 1. 3 over 3 reduces to 1. And when we multiply by 1, that doesn't have an effect on the answer. And you can see what ends up happening is we get just the 4 factors that we originally laid out on our blanks. So this formula gives us a notation to use and a way to calculate it. Now for this course, I am going to allow you to use your calculator to do the calculating. However, you would need to show work, and your work would be what's the thing that you're typing into your calculator. Now, it is possible in some situations that your permutations have repeated objects. They're known as the distinguishable permutations. If you have repetition of certain things and you can't tell the difference between them, that reduces the number of ways that you can organize them. For example, suppose I want to arrange the letters in the word set. Well, I can leave them in the current order. I can leave the S first and switch the next two. Or maybe T is first, followed by E and S. Or T is first and I switch those. And finally, I can start with E and then switch the order up of the S and the T. I can see that these arrangements are all different from each other. Only one of them actually spells an English word. The rest are basically gibberish. So there are a total of 6 different ways that I was able to organize 3 letters. And that's because I had 3 spots to fill, 3 choices for the first spot, and then 2 and 1, giving me 3 factorial, which is 6. Now, if I was taking the word C and asked to write out all the different ways you can organize those letters, well, C like this and C like this are not distinguishable. I can tell you, oh, this E was first and this E was second, and this time I switched them, but you can't actually distinguish a difference. So once I put the word C on my list, I'm not going to put C with the E switched. I can't tell the difference between those. So if I want to arrange these 3 letters where I have a repeated object, I only want to count the things I can distinguish. So SEE is clearly a different arrangement than ESE, which is clearly a different arrangement than EES. There's no other ways that I can do this. And the way that you would calculate in this case is you pretend as if all of your letters were distinguishable, which was 3 factorial, was the different ways we could represent the 3 letters. And you're going to remove some of those possibilities because we can't distinguish them. So that involves doing the opposite of the multiplication rule. We're going to divide out some of the possibilities. And what you need to divide out is you want to identify what repeats and how many times. So in SEE, the letter E repeats and it shows up twice. So what I'm going to do is put that number of repetitions in the denominator as a factorial. And if I do 3 factorial divided by 2 factorial, meaning 3 times 2 times 1 divided by 2 times 1, reducing everything that becomes equal to 1, you can see I'm left with the correct answer, which is there are only 3 possibilities. So in summary, if your objects are all distinguishable, then you're just going to do the basic factorial notation or use the NPR. If you cannot distinguish between objects, then you need to reduce the number of possibilities that you can actually distinguish, and you do that using division. Now, a classic example of this is using the letters of the word Mississippi. How many different ways can we rearrange those letters? So you're going to look and you're going to say, oh, yeah, I can't distinguish these S's and these S's or these I's and these P's. So therefore, I'm going to take the total number of ways that I can arrange this many letters, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And if the letters were distinguishable, 11 factorial would be the ways that I could arrange them. However, I can't distinguish all of them. S is one of the letters that repeats, and it shows up 4 times. I is a letter that repeats, and it shows up 4 times. P also repeats. It repeats twice. So, as I started to say before, when you need to reduce the number of possibilities because some are going to look the same, you'll always use division. And then in the bottom of this fraction, you are always going to line up a separate factorial for each kind of thing that repeats. In other words, I'm going to put 4 factorial in the denominator first to represent the s's being indistinguishable. Then multiplying that, I'm going to put a factorial for the number of times that I repeats. And then multiplying that, I'm going to put a factorial for the number of times that P repeats. So if you have multiple things repeating, this is the way you're going to set this up. Now, typing this into a calculator, you must put these parentheses in. If you do not put parentheses around your denominator, you will get the wrong answer. So please be careful. And when you type it in on, a single line display, it would look like 11, put in your factorial symbol, put in your division key, and then in parentheses, you're going to do 4 factorial, whatever your times key looks like, 4 factorial times 2 factorial. Okay, so you should try this on whatever calculator you plan on using for this class. And the correct answer should be 34,650 different ways. If you leave off the parentheses, I'm getting the number 79 million, okay, which is way too high. When you get things that you can't distinguish, it should always reduce, make smaller the amount of possibilities that you have. All right, now example 4 does come to you from the book. It says a building contractor is planning to develop a subdivision. It's going to consist of 6 one-story houses, 4 two-story houses, and 2 split-level houses. And how many distinguishable ways can the houses be arranged? So the first thing we would need to know is how many houses are we looking to arrange total? So we have 6 and 4 and 2, or a grand total of 12 houses. So if we could tell them apart, if I had told you it's 6 one-story houses and one is blue and one is green and one is whatever, if we could distinguish, there would be 12 factorial ways to arrange those. However, there are some we can't distinguish. So if there are 6 one-story houses, one story is one type of house that's going to repeat, and it's going to happen 6 times. Two-story houses, there will be more than one of those, and we're told that's going to happen 4 times. And then we have split-level houses, and there will be 2 of those. So I need to reduce my total number of possibilities, always using division, and I need a separate factorial for each one of these items that repeats. So again, I've got one for 1 story, one for 2 stories, and one for split level. I'm going to make sure I always put my denominator in parentheses. And if you go to a calculator, type that in properly, you should get 13,860 different ways.